here for another month, so you can ask him plenty of time to ask more questions. Okay, so he'll show us or tell us about how edges of graphs can cross in space. I don't understand how this can be the case, but he'll explain this to us, right?
Sure. So thanks for the invitation, for the long-term invitation, and thanks for organizing the Discrete Geometry Day. So I'm going to explain to you how graphs have crossing numbers in space, which sounds like a silly thing. So I'm going to consider my graphs are going to be one simplicial complexes. That you just think of the edges as represented by segments and the vertices represented by points. And well, of course, if you just draw that in 3 dimensions generically, you won't have any two edges crossing. So I need to give you a definition of what is a space crossing. So let me first go what's a crossing. So a crossing is similar picture. I have a graph and I draw it into the plane. And a crossing is what I draw there is two edges that intersect in the interiors. And now, what's the crossing number of an embedding? You just count the number of such things. And what's the crossing number of a graph? You consider all possible maps. You count and you consider the crossing number of each map, and you take the minimal one. So that's the definition of the.
This is the rectilinear crossing?
No, this is just for topological maps. So the edges are drawn by continuous curves.
Okay. It's just a new picture.
So, yeah, it's easier to mistake that. But yeah, f is just some continuous function.
Yes. Yes, and I'll go to the definition of space crossing, but first I motivated. So in this picture, I want you to think about these two edges intersecting. I want you to think about that as a zero-dimensional space, namely the point where they intersect, being transversal to these two edges. So that's what I think about. That's a crossing for me. So I just say different words for the same thing, obviously. So this point, think about it as a zero-dimensional space. And now I can tell you what's the analog in 3 dimensions. So I map my graph, and now I'm going to look at edges. And here I want to be more precise than in the previous definition. I want them to be vertex disjoint. So this is a 4 tuple of edges. So these are 8 vertices with edges between 4 such pairs. So that when I drew my graph, there was a line, a 1-dimensional space crossing these 4 edges. So this is the picture when I look at these 4 edges from the point of view of that line.
All edges are segments.
Yeah, but in this picture they're rectilinear, but then I'll talk more generally about curves. And then, right, so is it clear what a space crossing is? So I draw my graph, it's in R3, and I call something a space crossing. There are 4 edges, and there's an extra line that goes through the 4 edges, intersects all 4 of them. And these edges have to be vertex disjoint. So that's a space crossing. And then you play this thing again, you define the space crossing number of an embedding, and then you define the space crossing number of a graph to be the minimal among all embeddings, the minimum among all embeddings. So it's not obvious at all that the space crossing number of a graph has to be not 0. That's already, I don't know.
So it's not related to crossing number?
Yeah, it will be related to crossing number in the plane, but it's not that easy. I mean, yeah, you'll see. And then I'll define this other thing. So I'll denote it by CR. So for G, that's the crossing number, and if I put min before, that means that the graph is drawn by, the edges are represented now by rectilinear paths. Okay? So I have two quantities. One is for all topological maps, and one is for rectilinear maps. Phaseways are fine.
It's a minus or a dash?
It's a dash. It should be a dash. And then what I want to do is I want to copy I want to mimic what is known about the crossing number. I want to take all the theorems that are there for the crossing number, and I want to do it for the space crossing number. And then I want to relate it to the crossing number directly. So what are these theorems? In my point of view, the two main results are this crossing lemma, which is an old result from the 80s. And two of the names are... okay, so it's Samarelli and two other authors. It was published by them, and then Lighton also published this result. This was proven independently by these two people. And what it says is the following. If you have a graph and it has many edges, then it has many. Then no matter how you draw it in the plane, you will get many crossings. And it says it in a very particular, you have this very precise quantitative way. So this inequality is typed, which means that for any number of edges and number of vertices of a graph that you give me, I can construct a graph and a mapping into the plane so that the reverse inequality holds true asymptotically. And there's a whole industry in finding out what these constants are. Okay, so notice that I'm assuming that the edge set is not too small for this inequality to hold. In particular, if you forget about this and you consider a tree, this will be obviously false. So that's the crossing number inequality, and it's very useful to prove, for instance, the Samarelli-Trotter theorem and the incidences and so-called Erdős-Hart problems. It has a lot of applications. So that's one inequality that I would like to generalize. The second one has to do with the sort of isoperimetry of the graph, or the expansion or bisection width. I wrote it with bisection width. So what this says is that, so what is the bisection width? You take your graph and you partition the vertex into two pieces. And now the bisection width is, among all the ways to partition into two pieces, the minimum number of edges that go between these two pieces. So it's somehow like the isoperimetry of the graph, and this inequality says that if the bisection width is very different from the one from Euclidean space, then you would have a lot of crossings in any drawing into the plane. So our main result would be a very nice realization of this inequality that almost implies it. And for this one we cannot prove it, but we can prove something. So if you look just at graphs that have really large bisection width, namely pseudo-random graphs, or in particular random graphs, so expanded where the expansion is as high as possible, then so this is a large slide. So in that case, we can prove. I think the only thing important here is this. So let me state it. If I have a pseudo-random graph and I map it rectilinearly to 3 space, then I will get many space crossing numbers. As many as the number of edges to the 4th, which is as much as you can expect. Is it clear what I'm stating? So let me say it one more time. If I have a pseudo-random graph, no matter how I map it to R3, if I draw the edges by line segments, then there will be many 4 couples of perfect disjunct edges that have common transversal length. So here's the previous ones on this same type lemma, which is a bit hard to read, but I'll explain it with pictures. So that's my map. So if you think about it now, once I told you where the points are and which points have edges between them, I told you everything about this map. because they're drawn by rectilinear maps. So here I draw the vertex set in space, and now you haven't drawn the edge set, but it will appear at some point. So now what the same type lemma says is that I can find subsets, little subsets, that look like this. So here are 12, and they have the following property. If I choose one point of each, and then I choose furthermore 8 points of each, and not only I choose 8 points of each, but I match 2. So I have this 12, and I chose a matching of 8 of them. So that will give me 4 segments. Then if there's a line between these 4 segments, then when I look at the blobs they belong to, there are all these lines. So this is what the same type lemma gives me. So let me do that again. So I told you my point set, and I subtract small point sets. And the point is that they're kind of small, but they're not too small. Namely, they're a constant fraction of the total size of the set. This constant fraction is tiny, but it's still a constant fraction. So if you think of the number of points going to infinity, this is really large. Although it's a tiny fraction. And okay, so then I choose some edges, and if there was a line going through these 4 edges, then for every 4 tuple, 1 edge from here, 1 edge from here, 1 edge from here, and 1 edge from there, there will be a red line. I didn't draw all the red lines because that would look really red. Okay, so now how do I use this? I draw K66. That's K66 on some representative of my blobs, and I will prove to you, or maybe I won't prove to you, but I will state the theorem saying that the space crossing number of this graph is not 0. So that means that here there must be 1 transversal to 4 disjoint edges. And now this means that if my graph contained all those edges, then I would have all these transversals. But my graph is a pseudo-random graph, so I know that I have some fraction of those edges. And this completes the proof. Are there any questions about this proof? Alright, if there are any questions, well, I mean, the magic step was this, which I will talk about in a bit.
And the same type lemma just guarantees that one such witness of this one transversal line means that
There's
all
many.
of these.
Yes, there's many of them. So this works for dense graphs, and it works for pseudo-random graphs, but only for those. Okay, so now addressing your question, I have that inequality. So the space crossing number is less or equal than the number of pairs of crossings. Can anyone prove that inequality for me? It's just one idea. So more precisely, if I give you a drawing with a certain number of crossings, I want you to produce a new drawing, the known space, with such that a space crossing corresponds to 2 crossings in the planar drawing. Anyone? Alright, that's it. You just put it on the sphere. And now what's a crossing? Well, what's a space crossing? If I have a sphere and it's crossed by a line, then it crosses in exactly 2 points. So at worst this was a crossing and this was a crossing. So I get exactly that picture. Okay, and this is the analog of the space crossing lemma that I advertised at the beginning. Notice that I have this logarithm here, and I think that shouldn't be there, but we don't know how to get rid of it. And Boris says this is the main result, and I agree with him. But now notice something that's kind of cute. If you take our space crossing lemma and we take the inequality that I just showed you, you get this, except for this log factor. You just plug in play around with those two equations, and I mean basically I'm just saying that this number squared is that number if you forget about the log. And I told you that this inequality was tight, so up to the log factor that I don't like, that inequality is tight. But you could complain. You could complain and say, well, but your drawing is it's not really in space, it's kind of in a two-dimensional. So we constructed some graphs that are drawn with rectilinear edges that show that this inequality is tight. And I mean, this is a very nice idea, stirred convexity of Boris, and he has written a couple of papers on the subject. So I encourage you to read about it, but I won't talk about it at all because then guess I heard a talk by Boris, and he realized something really simple. If you just take a union of cliques, so these are cliques, and you draw them really small in general position in R3, and you just count, you get precisely the type bound. So I won't count for you because Andreas told me that it's not polite to do that in public. But it's really easy, you just have to do like basic combinatorics. Okay, and so this is the result I stated before here, and this was sort of what inspired the whole work, this result of, I can't say this name. Would you help me, Leslie? Yeah. Okay, I can't pronounce Serbian, and people have made fun of me. Huh? Thank you. So that's the result that inspired this thing, and if you just use that and you apply the usual probabilistic method trick that you use to prove the Krasov lemma, you get this inequality. Notice that this inequality for dense graphs is tight, but if the graph is not dense, this is not tight. So we work a little bit more to get the other inequality that I advertised before. Okay, so I'm going to use a couple of theorems now. So first of all, I need this theorem by Conway, Gordon, and Sachs. This is also from the 80s. And it says that if you map K6, the complete graph on 6 vertices, into 3-dimensional space, there are 2 triangles that are linked. At least 2 triangles that are linked. So remember that. And this is a result that is sort of a quantitative version of an old result of matter, which says that for any small graph, did I call it something? Okay, so maybe I'll write it here. So this is a theorem. This is a generalization of the theorem of matter. I think this is matter. So the theorem says that for every graph H, there exists a constant C of H, such that if G is another graph with the number of edges G larger than that constant times the number of vertices of G, then H is a topological minor of G. That's a theorem, and this will be a very useful tool for us. So it's a statement here. So it only says if you have a graph and it has large number of edges, then you can find any minor that you wanted of a constant size graph. And this is a refinement of it, so here the constant is quite big, and then instead of getting one, you get many. Many which are edge disjoint. So this will be important for us, that they are edge disjoint. And the proof, you just have to do this proof, but be careful with how many edges you're using in each topological minor, and then just repeat it on itself. Okay, so if you put them together, you start with a graph with a lot of edges, then you obtain all these edge disjoint minors, K6 minors. You apply this theorem for K6. Sorry for not specifying that. And each one will give you two triangles that are linked, and all of these are edge disjoint. So at the end, I obtain a lot of these links distributed among my whole graph. But let me step back a little bit. So I start with my graph, and I partition it in half. Half of vertices to each side, and I forget about the edges going in the middle. And all that I want is that the density in both sides is more or less the density of at the beginning of the graph. And you can do this very easily. Then apply this Costacha fever with the Conway-Gordon result on each side. And now you get many links on two sides. And for each pair of links, you get one space crossing. Why? Well, I need to tell you why. Because of this theorem of Vera. So what it says is that if you have 4 loops, this is just a topological statement, if you have 4 loops in space, and 2 of them, like in this picture, these 2 are linked and these 2 are linked, then there's a line going through the 4 circles. So we didn't know that Vera had proven this, so we proved it again, and her proof is kind of short. Her proof is really long, it's like 30 pages, and her proof, I'll explain it in a second. So that was kind of nice. So if you, I partitioned this, and I have that many number on top of minors, and then I have the square of that. That's what I got here. Yes, I don't know if that was clear enough. So I started with my graph, I partitioned it into 2 pieces. I applied the Conway-Gordon and Costacha fever on each side. I get all these links, and each pair of links gives me a space crossing, and if you do the counting, you get this inequality. This inequality, as long as this inequality is true, as long as you still have, your graph has enough edges.
So how does the load factor coming? Is it because of the Costacha primary
Yes.
load factor there?
Yes. So when you take these minors, you want to make them of small diameter, but there are examples in which they can be of diameter log of b. So that's one. Okay, so now I have this inequality, and from this inequality I want to get to the other inequality that I told you about. So that's in the next slide. So this inequality, that lemma 22, that inequality is true whenever I have that condition, whenever my number of edges is not too small. So if you think about it, you can summarize that whole statement with the following inequality that I stated for G prime. Why? Basically, when that falls on the right, this quantity, so when E is less than that constant times the number of vertices, this quantity is just negative. I set it up so that this is true. And so this inequality right here is true for all graphs. So now I start with my big graph, call it G, and G prime is going to be a random graph, a random subgraph, a random induced subgraph to be precise. So I choose each vertex inside it with probability P, and I take the induced graph, and then that inequality is true for that G prime. And then I take the expected value on both sides. So here you lose a little bit in the constant because this is not linear, but basically you're using linearity of expectation plus Cauchy Schwarz or something. Jensen inequality, I forget. But all in all, you get this inequality. So this holds for every P, which is a probability, and you optimize P for this to be best possible. P has to be a number between 0 and 1, and that gives you this condition. And that finishes the proof. Are there any questions about this proof?
Can you write down the number C and C capital explicitly some, at least some numbers? Because above there are very explicit numbers.
Yes. So this C is roughly this, I think. And this C
Capital. Capital C may depend on the probability P. Right?
Yeah, the capital C, exactly. You just need to, so divide by P to the 4 and then optimize this. So divide here by P to the 4 and optimize for P. So it's not too bad, I think. It's not too good. It has to be in the range of all the constants that I have inside. So my guess is less than 4 to the 100 to be on the very safe side. Okay. Any other questions? So I promised to show you a proof of this theorem. So as I said, there was I think it's a PhD thesis, and it's a bit long, and it's a lot of approximation. It's very nice, but there's a lot of argument that you're like hand waving. So first let me explain the idea. So I have my two links in space. This could be weird. I don't know. This could be good. And I want to show that there's a line that pinches this circle, this circle, this circle, and at least one point. So what's the idea? Here's the sphere, and for each direction I'm going to project into this plane. Okay? So I project those two links into this plane. So I'm just projecting orthogonal to this vector. These two links. And since they were linked, then I will have some crossing here. So I look at the vector going from one to the other one. And this defines a field on the sphere. And so now I move around the vector, and well, the Harry Ball theorem tells me that this cannot be vanishing.
It must be that.
This can be non-vanishing, right? So there has to be a point where it vanishes. And if you think about it, a point where it vanishes, it means that these 2 points were the same, which means that in the projection they were aligned. But this proof is wrong, because this is not containing errors, and it's a bit of a mess. So you have to work a little bit more. So that's why I wrote there. But essentially this proof is correct. So I'll just explain. And this idea is from a Soviet mathematician whose name I can't say properly. So now I'll explain the actual proof. So maybe I can use this. What's wrong with it? Oh, this identifying the crossing here is not continuous.
There are several crossings.
First of all, you have several crossings, but also, yeah, at some points these two crossings are going to meet and then they're going to separate. So this map is not well defined as I described it. But, I mean, what I'm gonna do is sort of use homology to say exactly the same thing, more or less. So I'll try to convey the idea. So, I think about these two things as, so I have four maps, C1, C2, C3, this is too small. Oh shit. Okay. I'll do it again here, C1, C2, C3, C4. And these maps go from S1 to R3. So these are the images of those maps. And what I know, okay, give me 1 second. Okay, so let me write that again. C1, C2, C3, C4. From the sphere, from the circle to R3. And I know that the linking number between C1 and C2 is not 0, and the linking number between C3 and C4 is not 0. So first of all, what does this mean, the linking number? So this is just, you consider the following map, so-called Gauss map. So let's do G12 or G1, and let's define G1 to be just, so this is C1 minus C2 divided by their norm. And similar G2 for 3 and 4. So, in this picture, I'm taking a point here, and I'm taking the direction to a point here. And I'm recording that in the sphere. Okay? And I'm thinking of that as a map from the torus to the sphere. And similarly for the other links there. Okay. But now these maps are going to factor to the following map. So H1 is going to be a map that you should think of, instead of recording just this vector, I want to record the whole line. Okay? So this map is going to go from, again, the torus, but it's going to go to the space of lines in R3. And a good way to parameterize the space of lines in R3 is by the tangent space of the sphere. This is the space of directed lines. So how does this work? Let me go back to this one. It's very similar to what I drew before. So for, say, take this vector, look at its tangent plane, and a point here corresponds to the line parallel to this vector that passes through that point in this particular plane. In this way, I have a parameterization of lines in space. And so this map is just, so the map H1 is just the point in tangent space corresponding to that line. So I didn't quite finish defining a linking number, I'm sorry. So the linking number is if you look at G star in homology, so G star now goes from H2 of S1 plus S1. No, let me not say that. Forget about that. The linking number, so linking number of C1, C2 is just the degree of the map G1. So that's definition of linking number. Okay. So another way to say that, which maybe I'll write here, is that what I was writing before, U1 star of S1 plus S1 equals the linking number of G1, sorry, of C1, C2, times the class of S2. This is in homology. So I'll use this in a second. Okay, so I define this map. It takes a point on the torus and it defines a line corresponding to the transversal line of these two circles. And see now that there's an H2 for the other two links. And what I want to show is that for some point in this torus, H1 equals H2, no. I want to show that the image of H1 intersects the image of H2. Yes? This means that there's a line through both of them. So now I want to recall the Thom space. So the Thom space is, should I recall the Thom space? Let me be a bit hand-wavy here.
So if you want to use one variability, then you have to recall Thom space.
I do, right? Alright, so, yeah, I have done. So Thom space. So whenever you have a bundle, so little Thom construction. Whenever you have a bundle, you can look at this bundle. So by a bundle I mean a vector bundle. So what's a bundle? Is you have a base space and on top of this base space, on top of each point you have a vector space here. This is RK. And this bundle it just means take a little neighborhood around the zero section. So the zero section is each of these points there's a zero on top, that's the zero section, and you take a disk around it. So that's the disk bundle, and the sphere bundle is just, well, this sphere, sorry, not this, but this sphere. Alright. So I want to show that, the image of H1 intersection the image of H2 is not zero, is not empty. And what I'm going to do is I'm going to look at H1 and H2 are defined in the disk bundle, because if I take this disk to be really large, the image is contained, because this is just a compact set. So I'm going to take this disk bundle and I'm going to collapse all the sphere bundle to all the points in the sphere bundle. I'm going to collapse to a point at infinity. This is the Thom space of this bundle. And so this H, I'm going to think about it as defined as from this torus to that Thom space. Okay, and now I'm going to take Poincare duality. So Poincare dual to these two classes. I have two cohomological classes, and if the coproduct of those cohomological classes is not zero, then these two manifolds have to intersect. So these two sets have to intersect. And why is why are those two, why is the product of those two classes not zero? Basically, because of this condition. So, I sort of said that if I look at S1 cross S1 and I look at this H mapping here, and I put G here, there is a map that completes this diagram. So I define H and G, and there is a map that completes the diagram. And this, together with this, implies that the image of H1 in cohomology is the zero section. So this is is homological to the zero section. It's homological to the zero section. Let me write it like this. And so if I take the comparable of the zero section, this is known, this is the Tom class. And so I'm trying to show that the Tom class with some linking numbers here, linking number of C1, C2 times linking number of C3, C4 is not zero. But it turns out that this Tom class and Tom class is the image of the Tom, is the image of the order class under the Tom isomorphism. Okay, so this is called the Tom isomorphism, and I know that what says that it is an isomorphism. So I just need, if this is not zero, then this is not zero, then this is not zero, then these two things intersect. But I said this was an automorphism, but the Euler class of the sphere bundle is not zero. This is well known. In fact, if you evaluate it on, if you think about it as a cocycle and you evaluate it in the sphere, this is exactly the Euler characteristic. So, and that completes the proof. So I said when I did the first argument, I said that this was essentially correct, that we had to do some work, and this is what I mean. At the end of the day, it boils down to this other characteristic being not zero, which is the same way that you prove the other thing. Okay, so I hope that was not too boring or confusing. So you might wonder what happens in other dimensions. You might wonder what happens if you embed graphs in higher dimensions. Can you define similar such invariants? And the answer is yes, and our results generalize. You can prove this crossing lemma in any dimension, and what we need for the higher dimensions, we were working on it, and then we realized that Karashov had already solved it, and he has many other results in this paper. So what substitutes all this topology, he already did in other dimensions. And with this, we get pretty good space crossing numbers for all dimensions. However, you might wonder, well, that's embedding a graph in higher dimensions, but what happens if you embed a complex into higher dimensions, so a two-dimensional complex or a higher dimensional complex? In that case, for dense complexes, for complexes which have a constant fraction of all the possible faces, we can also use Karashov's results. And for pseudo-random complexes and phase-wise affine maps, we can use the same type lemma. So those are the things that we know. But then this really annoying questions There's no analog. The main thing that we're lacking is an analog of matters theorem that I wrote on the board and then I erased. And we don't know if you have a complex with endpoints, end vertices. How many triangles can it have before it becomes non-embeddable in 4 dimensions? This is a very annoying question. It's a very interesting question, I think. That sort of finished what I wanted to say, but I'll give you an appendix. So there's these theorems by Kolmogorov and Warjin from the 60s, in which they have a sort of similar-looking, philosophically similar-looking problem, but it's sort of very different at the same time. So what they do is, again, they consider graphs, and they map them into 3-dimensional space. And now, what they want, so we found these sort of crossings, which are alignments of edges. What they want is they want all the edges to be a distance at least 1 apart. So I want to define thickness 1 map to be one in which for any 2 vertices, the distance at least 1 apart, and for any the Euclidean distance. For any 2 vertices, they're a distance at least 1. For any 2 edges, they're a distance at least 1. And for any edge and vertex that is not on that edge, they're a distance at least 1. So this is a thick 1 embedding. And they prove 2 things. They prove that if you take a thickness 1 embedding of any graph, you can embed it in you can make it inside a ball of size some constant times square root of the number of vertices. And they also prove that for pseudo-random graphs, you need that amount. So let me say this intuitively. If you take an expander and you map it into R3 in such a way that 2 edges are a distance 1, every 2 edges are a distance at least 1, then you need a huge ball to contain this. It's kind of funny because I mentioned that later when he started studying the crossing number, he was interested in BLS design, so designing circuits. So if you're designing circuits, you don't want many crossings because then your circuit starts growing. And in their introduction, they were motivated by similar kind of questions and by the brain. They wanted to understand. So Kolmogorov wrote that the neurons in the brain are sort of in the surface area. He wanted to know combinatorially how many connections they have and stuff like this.
Here, segments here are edges here are segments.
No, any mapping. They can be. They don't have to be rectilinear.
Any wires.
Okay.
Any wires.
Has application in brain.
Has application in the brain, yeah. And the second part of the theorem is that, I mean, not only you need a big ball to contain this, but actually this ball is pretty much filled in. Right? So it's not one direction that makes you go. This ball is filled in. So I'll show you, and that sort of implies the first one. So I'll show you how that proof goes to finish this. Oh. No, that was my last time. So I think I have to go to the board again. Okay, so I'm going to need a theorem of outcome there that says that if you have an open set in Rn or closed set in Rn, and then let's make it up 3, and k is bigger than n halves. Then there is a family K-planes, each be such that the K-dimensional volume of HT intersected with my set is less than some constant times the volume of U. This is the n-dimensional volume of U to the n minus K over n. That's a theorem that I'm going to use. Right, so there's some direction in which you don't intersect too much k-dimensional heavy. And this is exactly of the right. And notice something funny. K has to be bigger than n halves. So I wonder if this n halves is related to that other n halves of the problem I can't solve. The number of simplices. I doubt it, but it could be interesting. Okay, so now consider, let G be an expander, or a pseudo-random graph. Maybe I just need an expander. So namely, if I have sets A, B, such that their union is the vertex set and each one has size bigger than, say, 1/3 times B, then the edges between A and B are bigger than some small constant times Yeah, this is not the best way to define it. So that's your definition of the definition that I'm using for it, or the property that my graph will have. So now imagine that the proof is actually very simple. Imagine that I map such a graph to R3. I apply this theorem with K equals 2. So I have my graph here. It's a vertex set and there's some edges. And so, So this is my graph, G, and I take the neighborhood of G of size 1. So every point that is a distance at most 1 from the image of my graph. And that's what I've drawn there. And this is going to be U. And I'm going to apply that theorem to U. So what does that give me? This gives me a family of planes, or a direction, such that all the planes intersect not too much area of this set. And I'll move this plane until I pass half of the vertices. Now I have this plane. So this plane is having the vertices. And now I look at the intersection. So the property of this graph, there has to be many edges in that intersection. So I just draw what I see of those edges, which is just a point for each. And for each one, I have to have a ball of radius 1, right? Or sorry, radius 1/2. So that this distance is at least 1. And so I have the following inequality. Volume of U to the 2/3 is bigger or equal than the two-dimensional volume, or also called the area of this neighborhood of size 1 of G.
might be 1/3, no?
Sorry?
K is 2
K is,
and S 3.
K is 2 and S 3.
1/3. Volume should be 1/3.
Yeah, you're right. Okay. Oh. Yeah, you're right. Thanks. And this has to be, is this gonna work out? Yeah, I think this is gonna work out. And this has to be bigger than some constant times the number of vertices squared. This is square. But this is not what I wanted, is it?
Well, looks like the same, because,
Oh yeah, just,
yes, this is just a radius, if you want a sphere.
no, this is the actual sphere. No, this is fine, sorry. So now just cross multiply. Volume of U is bigger than B to the 3/2. Right?
No.
No?
To the 6th, yes. No?
Oh. Wait, what happened?
Happens a couple of computations.
Yes.
This is why you shouldn't do computations in total.
Yes.
Okay, so maybe I miswrote the inequality here. If I have 2/3 here, then it's okay. That's B squared.
You need 4/3, no. A 4/3 is maybe too much.
No, I'm sorry. No, here's the problem with this pseudo-random graph. So this should be like that. This should be 1. Yeah, so this graph I want it to be an expander, so it can have quadratic number of edges. So this should be some constant times the number of vertices. Now this matches, and I guess
Yes, the 2/3 would be good, right?
2/3 would be good, so I guess here. We just like, okay, let's go check this out. So yeah, that's it.
Yes, now it has a proper dimension.
Okay. Okay. Thank you very much.